So hello, okay guys, welcome back to my biochemistry classroom. And today we are going to discuss a new topic, that is enzymes. And whenever you come across this term of enzymes, you very well know that the things which are containing ACE are considered to be enzymes because of their classification, which has been proposed by that enzyme committee. And they have classified into various groups like ethyl, oxidoreductase, and all that we will discuss later on. So basically, first concept is that these enzymes, they are going to be proteins. So these enzymes, let us take a blue color. So these enzymes, they are proteins. Okay, they are proteins. And there is one exception to this thing, that it's not every enzyme is a protein. There is one thing you must have come across in, I think, general principles of genetics. That is ribozyme. Ribozyme is not a protein, it is an RNA, but acts as enzyme. But acts as enzyme. Okay, so this point maybe they ask in the entrance exam. So all enzymes are proteins except ribozyme, which is an RNA and but acts as an enzyme. The second concept is that why we have enzymes. What is the main reason that we have enzymes in the body? There are various reasons. First reason is that they are going to lower the activation energy. They are going to decrease the activation energy. What is this activation energy? To make life easy, I will draw a graph for you, a simple graph, not a big mathematics graph. I know you came to MBBS because you hated mathematics and physics. So if I have a graph and this is the next graph, so I consider here time and I consider here a free energy change. What happens if I have a substrate at this point? I have a substrate at this point. This is my substrate. And this substrate molecule, let me make it a bit higher. So if I have a substrate molecule here, and to get converted into products, I have to reach here, blue point. So this is the substrate. This becomes the substrate. And this is my product. So the reaction, so what I have to do is I have to activate the substrate first. So for that activation, I have to reach here. So here my substrate is right now here to get converted into product. So normally, if I am doing this reaction without an enzyme, I would have to reach the slope and then go to the top of the slope and then come down to the product. Okay. This is my activation energy. This is my activation energy. This is my activation energy. But if I have an enzyme, the road which is followed by the enzyme is this. The route which is followed by the enzyme is this. So have I decreased the activation energy or I have increased the activation energy? You guys will tell me. I want to see your answers. So will I decrease? Have I decreased? This is my enzyme route. Very nice answer. So you have decreased. You don't need to climb this Mount Everest. You don't need to climb this Mount Everest. You can go from the hillside. Okay. So you can take an alternate route and this is done by your enzyme. So that is the meaning of activation energy, that we are decreasing the activation energy. So for this reaction, I needed some activation energy to convert my substrate into the product, but that activation energy was very high if I did not had an enzyme. But now I am having an enzyme, so my enzyme is decreasing the activation energy, meaning thereby I can go through a very shortcut route. That means I can liberate more products in less amount of time also. But to remember, one thing should be remembered, they are increasing the rate of reaction. So can I say they are increasing the rate of reaction, guys? Can I say they are increasing the rate of reaction? And you have to talk to me, because I have seen that bogus, people studying like this, sleeping also and studying also. I have to go for an active learning. Okay. You have to talk to me. This class is for you. It's an opportunity I give you all. Even if you are watching a video, I suggest you to talk to me. You give the answer. Utter it loud. It is for your benefit. Okay. So it's for the people who are watching my video. So that means I am increasing the rate of reaction. Can I say I'm decreasing the time? That is the concept also. I am decreasing the time of reaction. I am decreasing the time. Can I say at the same time? Can I say at the same time? I am, can I say that an enzyme can give me a triad? An enzyme can give me a triad benefit, I call it in my language. I call it it's not written in book, I call it a triad benefit. What is a triad benefit? First thing is that I am increasing the rate of reaction. That means I am getting the desired results in a very fast time. That means the second component of the triad should be decreasing the time of the reaction. That means I am decreasing the activation energy, which is a requirement for that reaction. So this is a beautiful thing enzyme is doing. Third concept to remember is that I want to make you I want you to make a note of this. It's not going to alter the equilibrium of a reaction. It is not going to alter the equilibrium of the reaction. Are you able to understand? So enzyme is increasing the rate of reaction by lowering the activation energy, but it cannot, I should say it cannot alter the equilibrium of a reaction. Are we able to understand? Are we able to understand, guys? Fine. So it has been seen that they can speed up the reactions. So I should write this. They can speed up the reactions up to 10 to the power, by a factor 10 to the power 6 to 10 to the power 11 times. They can speed up the reaction. Can you understand how beautiful these enzymes are? Okay. Yeah. Fine. So what is the question? No, equilibrium it cannot. The thing which is going in that direction will be going in that direction. That will depend now. Are you going in a reversible state, or you are going in forward state or a backward state? I hope you know these two arrows. So it is all based on the enzyme, what the enzyme is doing. So do you remember that we had phosphatase, which was going for gluconeogenesis? But if I had, if I was making a phosphate kinase, I was making a kinase, that was putting the reaction forward. I was going for glycolysis. Are you able to understand? So this is conceptual, orientation first. Okay. And do you know the beauty of these enzymes is that we are using it. It is said that about 30% of pharmacotherapeutic agents, no, enzymes are being used as drug targets. Okay, so enzymes are being used as drug targets, about 30% of pharmacotherapeutic agents. Okay, so that is what we call, in pharmacology also that rational drug design. Okay, so we are using what we are doing in rational drug design is that they are using some enzyme specific drugs. When you are making something, you are creating some enzyme specific drugs, you call it a rational drug design. Okay, so I should write it a rational drug design. Okay, guys, so this is the concept. Now the concept is that when I have to do an action, you are saying, sir, that we are going for a reaction, we are decreasing the rate of reaction. So that means enzyme should have some component. If it is a protein, it should have some site. It should have a site where I can bind my substrate and convert my substrate into product, because you are saying that it is doing everything for you. So if I draw, there is a famous diagram. Even if you check your book, standard international authors, Harper, etc., or even Lippincott, what they do, they make like this. Have you seen this diagram? This is a very famous diagram in your school days also. They make like this. But I want to add something today. Okay, I want to make something different, because you always keep looking at this active side, but you don't remember what is this. Now the concept is that, think that, when you go for, you are going for an ice cream. Okay, I give you a softie. Okay, yes, don't ask me the softie. Yes, okay, yes. So this is my cone. Okay, this is my cone, correct? And I am decorating this with a softie. Okay, I give you a strawberry flavor. Okay, yeah, okay, wow, what a softie. Okay, it feels that softie has Bell's palsy, isn't it? Yes, softie is having Bell's palsy, one sided. Yeah. So the concept is that, when you take the softie, what do you do for grabbing? You don't use your teeth. You never use your teeth. What do? You take your cute lips, isn't it? You take your cute lips, isn't it? See, guys, all people are happy. Sir, you said we are cute. No, you are not cute. But see, this is the cute lips. So this cute lips, you try to first start, you're psychologically, you are very much motivated towards, you have to eat this. Okay. And think that we have a class, for example, we have Saudi takes that softie and then he starts eating that, isn't it? So first what you are doing, you are taking your lips and then you are using your teeth for cutting. So that means your mouth as a whole is using as a grab. You are grabbing it, and then the main activity which is done. Yeah. The tongue also you can use for softie, but for my example, you can take as lips. Okay, yes. I know you eat it with that, you lick that with that tongue. Yeah, I understand. So this, when you're grabbing this cone, what we do is we are first grabbing it and then we are cutting it. Same way, this enzyme should have grabbing amino acids. They should have something to grab. That means if I make lips of this enzyme, let me make lips. This is lips. Oh my God. Upper labia, lower labia, and in the center, people are laughing. And in the center, I have teeth. I have teeth. The lips they are designed with, they are called as binding site. Isn't it binding site? Yes, sir. Yes, very beautiful lips. Yes. So this is a binding site. This is a binding site. Can I say this is binding site? Binding site. This is binding site. Binding site. Correct. This is a binding site. Correct. And this place is the place. This green place is the place which is the place for no catalysis. So catalytic site. Catalytic site. So how many sites you understand till now? We have two sites. One is a binding site. The central region is the catalytic site. Catalytic site. Okay, correct. Very nice. So that means this region is called the active site. So active site, this region is called the active site. Can I say active site is equal to, this region? I will dot this. This region is called the active site of this. So I can write active site is equal to binding site plus catalytic site. Is it correct or not? Yes, it is correct. So see, when we are studying slowly and understanding things, it actually starts loading into the hippocampus. We don't have to open it again and again. Should study only once. Think that you are studying it, for the last time. Correct? So active site is equal. I could have directly told you active site is what binding site, that all that, the way they are as if they are on the BBC, no, British Broadcasting Corporation. So it's not like that. We have to understand. Yes, so you can understand it as A is equal to B plus C. So if you have, if you forget sometimes, so very nice. A is equal to B plus C. Very good. Correct. Now the concept is that what, who is forming the binding site? That means they should be amino acid. So at the two lips, the upper lip is decorated with, how to decorate? I should take a sparkle, isn't it? So upper lip, no sparkles already used. I think girls use red. Yeah. So I should write it as, this is H, and the lower region is A. So H means histidine, and A means aspartate. Aspartate. And the teeth is serine. So histidine and aspartate are taking the softy, and to cut the cone, I am using a serine. So final activity, the catalytic site is the serine. Catalytic site is the serine. Are we able to understand? Very nice. So guys, you tell me as a common sense, you keep on mugging up in the books. I know you keep mugging up the concept. Why to mug up? Let's understand it. They write in the books, you must have come across in your, if you are mistakenly reading the books, I hope you are watching only videos, not reading standard textbooks. I hope that. But please supplement your videos with, you listen to my videos, they will be 100%. I will try to give you the best, but book reading is important. Okay, book reading is an important portion of MBBS. So book reading should not be, should not leave your books. So if I today teach you this enzyme, go home and open this topic from your book. That's how you can supplement your knowledge. Finish it today only. Okay. What happens? You see in the books, they write serine proteases. Have you seen? They write serine proteases. Yes. And I hope you know serine proteases. I have given you an this example. I have given you an example of the enzyme that is in the books written as chymotrypsin. Do you remember chymotrypsin or chymotrypsin, whatever you call it? Do you know chymotrypsin? Do you know? Yeah, very nice. So chymotrypsin is the enzyme which has this. So I have given an example of chymotrypsin. Are you able to understand? So this chymotrypsin, basically, I will tell you in the next story in some time. Chymotrypsin is written as, it is a serine protease. Serine protease. Must have come across this word. Serine protease. Yes, sir. Today we understand. Isn't it a catalytic site? Can't I write it as protease? It is doing proteolysis. It's a serine. So can you today understand why chymotrypsin is called serine protease? Can you understand today why it is called a serine protease? Yes, very nice. So, in some books, so how you remember, I discussed three things. I discussed histidine, I discussed aspartate, I discussed serine. These three are forming a triad. Okay. So, can I say serine proteases have catalytic triad is equal to histidine plus aspartate plus serine? Can I say that? Guys, can I say that? So they have same catalytic triad. Same catalytic triad. We call them what triad? You can write that. Aspartate, serine, and histidine. Aspartate, serine, and histidine. These are famous examples, we come across in the books. Proteases, serine proteases. So this is the thing you have to study. So there are other enzymes which can be serine proteases. We have more examples of serine proteases. Like we have, if I start with chymotrypsin. So let us write the examples. So examples are number 1, chymotrypsin. Number 2, do you know that when people we go for a prostate checkup, we go for a DRE examination. First thing I want to tell you, even when you are palpating, you are going for a digital rectal examination, you want to check the prostate. What we do, we put that index finger and we check whether the prostate, we go for transitional zone checkup. I will teach you that in surgery. So we are checking the prostate gland, we are palpating the prostate gland, because from the rectum we can directly feel that if there is an enlargement, so we can appreciate that. It's not, I want to make this point clear here. If someone is from a third, fourth year student, it's not that prostate specific antigen will be increased. Prostate specific antigen, can you understand? Sort of a thing, sort of an enzyme. So first I will write PSA, prostate specific antigen. Prostate specific antigen. So the problem is that what we do when we are in the wards and we are discussing a case of prostate, be it benign prostate hyperplasia or prostate carcinoma. What the notion I have seen is that people are understanding it as if PSA is only increased in, BPH, benign prostate hyperplasia. It's not that. Prostate specific antigen can increase even after sexual intercourse. After the sexual intercourse, PSA increase. You should write this. It's written in Bailey and Law surgery and even in Schwartz. So PSA increases in sexual intercourse also. And when you're palpating with the finger, that can also let the gland to produce some amount of prostate specific antigen. So doing after a DRE, you are checking a prostate specific antigen. You should be a genius, isn't it? You should be a big foolish genius, isn't it? So it's not, you will check, there are protocols that when to go for a checkup, when to go for palpation, where to go for examination. I want to make this point clear in this, in this video. Okay. PSA is also example of, serine protease. You remember elastases, they are examples of serine proteases. Do you remember the famous thrombin? Do you remember the famous thrombin? Thrombin is an example of serine protease. Even in that pathway we had plasmin. Okay, and clotting factors. Clotting factors. So clotting factors. 10 and 11. Okay. If you come across, they have seen that there's a research that when they studied some tumors, they were studying some tumors, and they saw the tumor metastasis is having a component of serine proteases. So that's why they say serine proteases are having some role in the tumor metastasis. So remember this. So serine proteases have some role in tumor metastasis. Tumor mets. Are able to understand? Correct? So this is the concept. Okay. Fine. So I hope you are understanding this. Now guys, when you come across, when you see the books, they write enzymes are having some components. Okay, enzymes are, and people are always confused that what is a cofactor, what is a coenzyme, what is a metal activated coenzyme, what is metalloenzyme. Are you able to understand? So I want to make the difference of all those things. What is an apoenzyme? What is a coenzyme? What is a holoenzyme? So let us today understand that. Okay. When you discuss about cofactor, no, enzyme is having some components. Enzyme is having some components. By the way, first thing I remember. Can you tell me if a substrate has to bind to an enzyme? So what things will be affecting that? Temperature. Temperature is going to be, it is going to be sensitive to temperature. So when you bind a substrate, when you bind a substrate to the enzyme, it causes conformational change in the enzyme. And at the same time, we have to remember that the pH, it is sensitive to pH, it is sensitive to temperature, it is sensitive to ionic strength. Are we able to understand? So yeah, okay. And remember one thing also, that enzymes, they are not going to change the concentration of substrate. So if the substrates and products are at equilibrium, enzymes are not going to change the concentration of substrates. I would repeat again. Enzymes are not going to change the concentration of substrates and products at equilibrium. But they will help you in achieving the equilibrium more rapidly. What did I say? I said enzymes, yeah, very nice, very nice. They speed up. So enzymes are not going to change the concentration of substrates and products at equilibrium, but they are going to help you. They are going to allow you to reach the equilibrium more rapidly. Fine. Second concept to remember is that there is no permanent change in enzyme during the reactions which they are going to catalyze. Okay. You may see some temporary changes, but yeah, they are not going to change. There is no permanent change. Yeah, temporary change may happen, but there is no permanent change. Yeah, exactly. Fine. Now, when I talk about coenzymes and prosthetic groups, see, enzyme, to make life easy, we will write like this. Enzymes are made up of protein part and non-protein part. Enzymes is equal to protein part, non-protein part. Protein part, please understand this. I hope you know this, but there are some, this concept, you think it is simple, but please understand some depth of it. Protein part is known as apoenzyme. Protein part is known as apoenzyme. Fine. Non-protein part, non-protein part. So first thing, when you see a protein plus non-protein part, we call this as, when you see protein plus non-protein part, we call this thing as active enzyme. We call this thing as active enzyme. Active enzyme, or it is also known as holoenzyme. Are we able to understand? It is called active enzyme or it is called holoenzyme. Correct? Now, non-protein part, I am not writing it directly because I want to discuss it here. So non-protein part, when I discuss non-protein part is having two types. It is of two types. Based on what? I will tell you a concept. If you are able to separate the non-protein part from the enzyme, we call it two types. We call it two types. You did not understand my point. We call it two types. So if you can separate The non-protein part, we call it two types. Are you able to understand? Never say directly. I'm saying they said non-protein part. So on the basis, I'm saying separation. They are classifying it as, understanding it in the form of separation, the bonding. So if you can separate the non-protein part from an enzyme, non-protein part, we say not a direct name. We again classify them into two types. If now see, first thing I will tell you like this. Let me say like this. I'm sorry. Let me say like this. If I can separate the non-protein part, first we should understand that is called a cofactor. That is equal to a cofactor. Correct? If you can separate a non-protein part, we call it cofactor. If you can't separate the non-protein part, we call it prosthetic group. We call it prosthetic group. Correct? This is first you have to understand. Now, if this cofactor, if this cofactor, if this cofactor, I am going so slowly today, so slowly to make you understand. Okay. Now guys, if this cofactor, now this cofactor, if this cofactor can be, I will make it like this. This cofactor can be, it can be one coenzyme. It can be one that is organic. Let us do like this to make life easy. It can be organic. It can be inorganic. It can be inorganic. Correct? If it is organic, we call it coenzyme. We call it coenzyme. But if it is inorganic and a metal, if it is inorganic, metal is the main component, then we call it cofactor. Since I told you it is having a metal, first I said it is inorganic. First you say if it is inorganic, we call it a cofactor. But if it is having a metal inside, we call it metal activated coenzyme. Metal activated coenzyme. Metal activated coenzyme. Correct? Let us go to cannot separated. Cannot separated, if I go, cannot separated is here. Prosthetic group, we said it is prosthetic group, and it is having inorganic prosthetic group. If it is inorganic, and in that inorganic he is metal, inorganic is metal, we call this as metalloenzyme. That is, metal is always with the enzyme. Metalloenzyme. Are we able to understand? This is a very easy concept. We have drawn a nice demarcation. We have understood it clearly. Are we able to understand? So guys, from this table, I can draw a conclusion. Can I write all coenzymes are cofactors? Can I write all coenzymes are cofactors? Yes, all coenzymes are cofactors. Is it clear from this table? So all coenzymes are cofactors, And from this table, can I also infer metals are cofactors? Look at the metal. Metals are cofactors, but not coenzymes. Metals are cofactors, but not coenzyme. Is it clear? Is this clear, guys? Can you understand this inference? Yes. Now, what did we say about coenzyme? Do you remember what did we say about coenzyme? We said non-protein part. Even. We can say non-protein part. So, the activity of, now I want to tell you why I built this, why there is a coenzyme, why there is a cofactor. See, the activity of some enzymes depend on non-protein organic molecules or metal ions, that is cofactor. So non-protein organic molecules, for example, coenzymes or metal ions, which are associated with this protein. Okay. Second concept is that, can I say coenzymes are organic compounds, organic non-protein compounds? You have to answer me. Can I say coenzymes are organic non-protein compounds? Because you are satisfying the definition of non-protein here. See, I am making it now clear. That bind reversibly to certain enzymes during a particular reaction. And can I say they are functioning as co-substrates? Yes. Now, guys, you know, when we were teaching you some, do you remember I was teaching you lipoic acid, I was teaching you NAD, I was teaching you FAD, I was teaching you FMN, I was teaching you FMN, I was teaching you B complex. Do you remember? And I said at that time that we can have coenzymes as vitamins. We can have coenzymes like nucleotides. We can have coenzymes like lipoic acid. Do you remember that? So same thing I am going to teach here what these coenzymes are. And there are some important points regarding that. If I say I have coenzymes, what coenzymes can I have? I can have nucleotides as coenzymes. I can have nucleotides as coenzymes. Let us write. I can have, so if I say about coenzymes, I can have number one, nucleotides as coenzymes. And I hope you remember what nucleotides I can use as coenzymes. I can use NAD. I can use NADP. I can use FAD. I can use FMN. But guys, it's not like every nucleotide you can use as coenzymes. There are some nucleotides that are not coenzymes. Like I have some nucleotide derivatives. Nucleotide derivatives. I have some nucleotide derivatives like SAM. What is SAM? SAM means S adenosine methionine. Do you remember it was a methyl group donor? Yes, this is that nucleotide that can donate. It can donate a methyl group, methyl donor. CH3 I can say. It is a methyl donor. It is a nucleotide, but it can't be used as a cofactor. It is not a cofactor. Sorry, it's not a coenzyme. It's not a coenzyme. Second, I remember PAPS. What is PAPS? PAPS is phosphoadenosyl. Phosphoadenosyl phosphosulfate. As you can very well see, it is a sulfate donor. 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 So can I ask you a question? Can you tell me Can I say all nucleotides are used as coenzymes? Wrong answer, false. All nucleotides can't be used as coenzymes. Why? Looking at what you said this, you saw SAM, S-adenosylmethionine. Sir, it is a methyl donor, but it's not a coenzyme. It is a nucleotide derivative, but it is not a coenzyme. We have PAPS. PAPS is phosphoadenosyl phosphosulfate. It's a sulfate donor. It is not a coenzyme. Are you able to understand? This is about nucleotide. Okay. So guys, I will be discussing in the next lecture. I will be continuing the discussion. Okay. So I hope you have enjoyed this topic. Please open your textbooks, standard reference textbooks, and have a look of this chapter from that. It will supplement your understanding. And another thing is that I'm uploading my lectures here also and YouTube also, so you can subscribe to this channel on YouTube also and invite more and more people so that they can get benefited. So guys, all the best. See you all tomorrow. Take care and bye bye.